Hi everyone, I'm Mr. Fullerton, and today I'd like to talk a little bit about Newton's second law. Newton's second law of motion may be the most important law we have in all of our understanding of traditional physics, of classical physics. Even more so, it is useful in so many different areas that it's certainly one of the areas we want to focus. And this is going to be a very short, brief overview of Newton's second law, but there's so many more things you can do with it. So we'll follow up with some other videos showing some demonstrations, some applications, and some other subtleties to applying it in various situations. So our goal for today, we want to explain the relationship between acceleration, force, and the mass of an object, which is really the root of Newton's second law. Then we want to apply Newton's second law to a number of different problems. We'll try and understand the difference between mass and weight, and finally we'll talk about static equilibrium and what current is. So, diving right in, Newton's second law of motion. It says that the acceleration of an object is in the direction of and directly proportional to the net force applied, and it's inversely proportional to the object's mass. If you wanted to write that mathematically, what you would say is the net force vector is equal to mass times acceleration. So if you apply a force to an object, the object is going to accelerate in the direction of that force. The bigger force you apply, the more acceleration. Now the bigger the object's mass, the less acceleration. And you see this all the time. Imagine trying to push a tractor trailer in a specific direction. It has a huge mass, so no matter how hard you push, you're not going to get much acceleration. Now try doing the same thing to a little matchbox car of the semi-truck. Apply the same force, and that little matchbox truck is going to have a huge acceleration, and that's in the direction that you are applying the force. So net force is also one of the key points. Net force means it's the overall force after you've looked at all the vectors. For example, if you are fighting with your sister or brother over a piece of Halloween candy, one of you pulls a piece of candy with the force of 5 newtons this way. The other pulls with the force of 5 newtons that way. The net force is 0. There will be no acceleration on the candy. It's going to remain just as it is. However, if one of you pulls with 6 newtons and the other pulls with 5 newtons, the person pulling with 6 newtons is going to cause an acceleration in their direction. Now also note, because we also have Newton's first law, an object at rest will remain at rest, and an object in motion will remain in motion unless acted upon by a net force. Just because something has a force on it does not mean it's accelerating. A satellite flying through space, let's put it way out in space, not even in orbit, flying through space. If you apply a 5 Newton force to it in one direction and someone else applies a 5 Newton force to it in another direction, it's going to just continue on as it was, continue its motion with no acceleration. You need to have a net force to change acceleration. All right. So, if you look at this, Newton's first law is really just a subset of Newton's second law. It's what happens when you have a net force of 0. If the net force is 0, the object will continue in its current state of motion, a constant velocity in a straight line. If you have an unbalanced force, if you do have a net force that's not equal to 0, then you get the acceleration in the direction. So, Newton's second law is more encompassing, a more general version. Newton's first law is just a specific case of Newton's second law. So if you understand Newton's second law, you really don't have to remember Newton's first law. To apply Newton's second law, we'll follow a set of generalized steps. Now, the first things you want to do is draw a free body diagram, and we've talked about how you make those. For any forces that don't line up with the x or y axes, break those forces up into components that do lie on the x or y axis. This is what we were doing when we talked about pseudo-free body diagrams. Then you're going to write expressions for the net force in each of the directions of the axis, in the x direction and the y direction, if you're going in 3 dimensions, in the z direction too. Then set that net force equal to ma, since Newton's second law tells you that the net force on an object is equal to the mass times its acceleration. Finally, solve the resulting equations. Let's take a look at some simple examples. We have a force of 25 newtons east and a force of 25 newtons west acting concurrently, that means in the same place and at the same time, on a 5 kilogram cart. Find the acceleration of the cart. Well, first we'll draw our free body diagram. There's our cart. We have a force of 25 newtons to the east and 25 newtons to the west. And let's call this the x direction, our x-axis. Therefore, the net force in the x direction is going to be 25 newtons in the positive direction minus 25 newtons, since that's in the negative direction, is equal to 0. And that must also be equal to mass times acceleration in the x direction. Of course, mass is 5 kilograms, therefore we can state that the acceleration in the x direction must be 0. There is no net force. They balance out. Let's take a look at another one. A 0.15 kilogram baseball moving at 20 meters per second is stopped by a player in 0.01 seconds. What is the average force stopping the ball? A little bit more complex here. So let's take a look. We're given the information that mass is equal to 0.15 kilograms. The initial velocity of the ball is 20 meters per second. The final velocity of the ball is 0 meters per second. And the time for all of this is 0.01 seconds. We want to find the force. Well, when I look at that, right away I'm thinking, well, Newton's second law, I have mass, but I don't have acceleration. So let's see if we can't figure out acceleration first. We can do that using our kinematic equations. Acceleration equals change in velocity over time, or final velocity minus initial velocity over time. That's going to be 0 minus 20 meters per second over 0.01 seconds for a total acceleration of negative 2,000 meters per second squared. All right, once we have that, now we can figure out the net force. Net force on the ball must be mass times acceleration, or 0.15 kilograms, times our acceleration of negative 2,000 meters per second squared, which is equal to about negative 300 newtons. And the negative signs in the acceleration and the force are really only saying that it's in the opposite direction of what we defined as positive initially. So the acceleration and the force are opposite the direction the baseball was initially moving. That makes sense because we're bringing it to rest. So our answer, 300 newtons. Let's try another one. Two forces, F1 and F2, are applied to a block on a frictionless horizontal surface as shown below. If the magnitude of the block's acceleration is 2 meters per second squared, find the mass of the block. Well, let's start with our free body diagram. We have 2 newtons to the right, and we have 12 newtons to the left. Now I'm going to pull out a little trick, and realizing that we have the larger force to the left, why don't we call to the left the positive x direction? We can call any direction we want to be positive, so let's try it this time and see what happens. Now when we write our net force equation, the net force in the x direction is going to be equal to positive 12 newtons, because that's in the same direction as our positive x, minus 2 newtons, because 2 newtons is opposite what we called positive, or 10 newtons. Now if we want to know the mass of the block, well, net force is also equal to mass times acceleration. Therefore, mass must be net force over acceleration, which must be equal to 10 newtons over squared our acceleration, or 5 kilograms. F net equals ma, another way to use it. Let's take a look at just one more here. A 25 Newton horizontal force northward and a 35 Newton horizontal force southward act concurrently, same place, same time, on a 15 kilogram object on a frictionless surface. Find the object's acceleration. Well, we'll start with our free body diagram again. We've got a 25 Newton force north. We have a 35 Newton force south. And let's call down our positive y direction in this case. Now, when we take a look at this, our net force in the y direction is going to be positive 35 newtons minus 25 newtons for a net force of 10 newtons. Now, to find acceleration, that must be F net over m, or 10 newtons over 15 kilograms, which is 0.67 meters per second squared. Now, of course, the direction of that acceleration must be in the direction we call positive or south, the direction of the larger force. It says magnitude. We don't have to write south there, but we understand what it is.